In this video series, you'll learn how to simulate a multi-phase flow consisting of air injected into a liquid-filled mixing tank. In part 1, we'll review the case, enable the Eulerian multi-phase model, and describe the phase interactions for this problem. I'll consider a simplified case in which there is no flow into or out of the reactor. This is a reasonable representation of the initial conditions in a real reactor at the start of a new process. From this simulation, I'll determine the reactor's quality of mixing and power requirements. At this point, I've loaded the reactor's mesh into Ansys Fluent. Let's start by reviewing the reactor's geometry and boundary conditions before setting up the multi-phase model. The geometry of this three-dimensional model represents an experimental reactor which comprises a Rushton blade turbine, a pitched blade turbine, a ring sparger, and 4 thin baffles. Note that since the aspect ratio of the tank significantly exceeds the normal value, 2 impellers are required for good mixing. The Rushton blade turbine's primary purpose is to disperse the introduced gas by providing shear. The pitched blade turbine mixes the bulk fluid by simultaneously pumping and shearing. Air is injected at the center through a ring sparger surface. The inlet's geometry ignores the presence of small inlet holes, and instead, the inlet is approximated as a uniform circular strip. Finally, baffles located on the sides of the tank prevent vortex formation. The boundary conditions for the reactor are as follows. The bottom and the side walls are defined as no-slip walls. The top of the fluid in reality is open to the air. The corresponding boundary in the simulation is modeled as an outlet with a degassing condition, allowing for air bubble release, which facilitates the application of the Eulerian multi-phase model. Now to set up the simulation. First, I need to specify the operating conditions. In this case, competition between opposing gravitational and buoyant forces influences the movement of produced air bubbles. To account for this, I'll include gravitational acceleration and set an operating density equal to that of the air. Note that for multi-phase flows, the operating density should be set to the density of the least dense phase. This warning message isn't cause for alarm. The degassing boundary condition, which was defined within the mesh, is not appropriate for the given set of models. I can fix this by adding the multi-phase model. Since the two phases, gaseous air and liquid water, aren't in equilibrium throughout the simulation, the Eulerian model must be used. Once I activate the Eulerian model, 2 phase descriptions become available in the phases subbranch. I'll describe the primary phase, which is the bulk fluid, as liquid water. The secondary phase is gaseous air. When the air enters the reactor, bubbles are formed. The size of these bubbles, which is related to the size of the inlet holes in the real reactor, is entered here. In this example, the hole diameter is 1 mm, so I'll assume a bubble diameter of 1.5 mm. Within the phase interactions menu, interactions between each phase can be described. In this example, drag between air bubbles and the bulk fluid is best described by the Grace model, which applies well to liquid-gas mixtures with low gas density and bubble sizes of 1 to 2 mm. I must also include a value describing the surface tension of the bubbles. Many different phase interactions such as lift, wall lubrication, turbulent dispersion, and turbulent interaction can be described here. However, for this case, only drag needs to be considered. Mixing in this model occurs primarily through turbulent fluctuations, so naturally I must add a turbulence model to this simulation. In this case, the standard K-epsilon model will do. Since the volume fraction of air in the bulk fluid is small, I'll use the dispersed multi-phase turbulence model. The dispersed model assumes the turbulence in the primary phase dominates, and the turbulent behavior of the secondary phase is approximated from the mean characteristics of the primary phase. Using these model settings, I could run a multi-phase reference frame simulation which provides steady-state data, or a moving mesh simulation which provides transient data. For my analysis, I only need steady-state data, so I'll set up the computationally less expensive multi-reference frame, or MRF simulation. This concludes part 1 of this demonstration.